Okay, good morning, everybody. I'm going to do things a little like Dr. Olubanu would do it, and then I'm going to fill in the rest of the hour with some things that I might do to cover these courses or this particular topic. So why am I not? Okay, so he gave me some sheets and told me that you were covering some derivatives of carboxylic acids. So I'm going to go over the things that he told me about, and then we'll look at some other aspects. So where apparently he left off was this reaction here, which is a reaction of an ester in which it reacts with water. And actually all of the reactions of derivatives follow a similar pattern. So all of the carboxylic acid derivatives react with water, and usually this reaction is catalyzed by acid. But there is also the possibility that you can work with sodium hydroxide, because sodium hydroxide is a good nucleophile, and these compounds undergo nucleophilic attack. So hopefully Dr. Olubanu told you, I hope you can see this when I start putting my hands in here, that the carbonyl group or the carboxyl group is polarized in such a way that the electronegative oxygen attracts electrons to itself, and that leaves the carbon electropositive. So then the nucleophiles will attack here. Now, if we don't have a negative charge or a very strong nucleophile, like OH is good, then what happens is that we need to use the proton H plus as a catalyst. So this particular reaction goes like this. The first step involves we're looking at the mechanism, the pickup of a proton by the oxygen. And then if we rearrange this, well now of course there is a resonance structure with the oxygen with a full positive charge. So that's makes it a good site now for a water molecule to come in. And that will then leave us with another intermediate. I'm not sure I'm going to have enough room here. So that intermediate looks like this. And here we have 3 oxygens now, so there's no reason why we can't transfer a hydrogen here. And actually this is an equilibrium process that can go in either direction. And if it does that, then we end up with positive charge here.
Would you be moving the page up?
Yeah, I think I maybe should shrink this down a little bit. I don't know. Oh no, that's the wrong way.
It might be the dial.
Yeah, it's up here. adjust the light. Actually, we can go out a little bit. Okay, so now, if we lose the alcohol piece, so that can happen by breaking this CO bond and giving back, or giving the oxygen back its electrons, then we end up with the following. And so the other piece is the HOR. And now all that has to happen is that we can lose an H+. And there are simple ways of doing it. This is sort of the simple way of writing that. And what we end up with is our alcohol and, excuse me, our carboxylic acid and hydrogen ion. Now, one of the things I've done here is I've written all of these arrows going in either direction. And in fact, I didn't do that one here, but I should. And in fact, the reaction can go in either direction. I'm hoping that probably Dr. Olubanu showed you how esters were synthesized. Is that right? Okay, one way to do it is to take the carboxylic acid and the alcohol and some acid and cook it up for a couple of hours. And water is split out. Where is it? Well, it didn't. Is it in my picture here? Here's water. So water is split out. So you can go in either direction. It's a complete equilibrium process. And the way that if you want to make the ester, you try to remove the water. So that will drag the equilibrium towards the product in one direction. If you want to break apart an ester, then you can do that by adding lots of water, and that will push the equilibrium in that direction. And you can write a similar reaction with hydroxide for the hydrolysis. Actually, that is the method by which Grandma made soap, because the fats that are used, or lard or whatever, is actually a triester of the alcohol, the trialcohol glycerin. Put that over here. This one's like that too. That one. And so there are, each one of these is esterified in a triglyceride. And in the process of cooking it with lye, which is hydroxide, this is broken down into glycerin and long chain carboxylic acids. They're the so-called fatty acids. And those compounds, the fatty acids, are simply carboxylic acids with long alkane chains. And it's because of that that the one end can be ionized as a carboxylate salt. So we have O, C double bond O minus, and then we have a long alkyl chain. So soap, as you probably know, is used for getting rid of grease. And the way that works is that the long hydrocarbon chain embeds itself in the non-polar grease, which is probably something like a long alkane itself. So like dissolves like attracts like. And then the other end can, because it's ionic, can interact with water. So that way you can lift oil out of clothing and things like that. So this process has a practical end to it as well. Are there any questions? Okay. The next reaction is a reaction in which we have ammonia reacting with an ester, and this process is called ammonolysis. Let me move this up. And it works basically the same way. So in this reaction here we have the ester methyl benzoate reacting with ammonia to make benzamide. And the mechanism is very similar. So here, ammonia acts as the nucleophile, attacks the carbon here, and then we end up with an intermediate that looks like this. Nitrogen now has a positive charge, and we can now transfer a proton. So we'll use that. See if I can get everything in here. CO minus, NH2, OH. So here's basically a water molecule over here, and if we take this pair of electrons and give it to the oxygen, that bond will break and we will separate out a water molecule. And actually that is, and then we can simply, we have to replace the number of electrons, so we'll take those from one of the three non-bonding electron pairs on the oxygen. And that gives us this, in this case, yeah, we have a methyl group, sorry, there's a CH3. That's the same. So now this is not a water, but a methanol. So we'll get methanol, and we will get an amide. Questions about that? I'm hoping that I'll be able to get through to some of the, try to tie these things all together for you. So here, the next reaction is one in which an ester again reacts with another nucleophile. In this case, the lithium aluminum hydride is the reagent. It's also a reducing agent, because we're going to go from a compound with an unsaturated carbon-oxygen double bond, and we will end up with an alcohol. So this is indeed a reduction. And the process here for this, if you follow along, what this will basically do is break down the molecule into two alcohols. So the left part will end up as RCH2OH. It's going to basically add a hydrogen to both of those two. The other one, the OR prime, will also end up as an alcohol. So the mechanism is very similar. The nucleophile here is a hydride ion, and you can see where that's going to come from because you have AL, H, H, H. So this is has a minus charge. It's going to give off one of those hydrogens with a pair of electrons. And when it does that, it's going to go back to ALH3, which is nice and stable. So, so here's the mechanism. Nucleophile attacks the electrophilic carbon. This is just actually this is what I consider to be a theme for many reactions in 252. Most for this course, I would say a large majority of the reactions that you encounter in 252 involve nucleophilic attack at a carbon-oxygen double bond. So this is a very common theme. And if you can follow the common theme, you're on your way to solving many of the mechanism problems. So here's what happens. Then the hydride's here, and in this case, then the alkoxide group is booted out, and now we have an aldehyde, which also undergoes, because it has a carbon-oxygen double bond, that then undergoes hydride attack again, and that introduces the second hydrogen. And what we're ending up with then will be an oxygen with a negative charge, and that will then pick up a proton from the acidic workup. Now, what do you think will happen in this case with this compound here? This is a compound that is a cyclic ester. Cyclic esters are called lactones. So here you have, basically, here's the acid part, and then there's an alkyl chain, and it wraps around the hydroxide, and the alcohol part is then connected with the acid part, and that is now completing the ring. So we would have the same process going on as we have up here, except that when we're done, we would have the, this part would be, you get this first of all, and then that would react further to give this diol. So that's what would happen. So the carboxylic acid end and the alcohol end are tied off in a knot. You can break it up, and when you do that, you'll get the same result. You get two alcohols, but they're in the same molecule. Now, one thing that you might want to do, you might say, okay, well, I like this idea, but I'd like to stop here at an aldehyde, because it might be useful to make aldehydes by a reduction. And so there is a way to do that. It's just that you have to go to the stockroom shelf and pick off a different reagent. This particular reagent for this reduction is a version of an aluminum hydride that has an aluminum, here's our hydride, and there are two isopropyl groups. So this is diisopropyl aluminum hydride. Oh, no, it's not isopropyl. It's isobutyl. Sorry, it's isobutyl. So this is the isobutyl group, and here's another one. So diisobutyl aluminum hydride, or DIBA for short. So here's a actually this is an ester. Here's a long fatty acid chain here. This particular fatty acid has 12 carbons in it. Here, the CH2 is repeated 9 times over. Well, actually here 10. And so it's a 12 carbon fatty acid that has been made into an ethyl ester. And with this reagent, we do get the reduction only to the aldehyde, and the reaction stops there. Questions about that one? Yes.
Would you get the same result as the last mechanism if you used two quantities worth
of DIBA?
Yeah.
No, it's tamer.
Okay.
So it doesn't go the rest of the way. All right. The last one is a version of a reaction that all of you would have done if you were in either 263 or 264 or 266 this semester. In that experiment, you made triphenylmethanol from phenylmagnesium bromide, and in that case, what was used was benzophenone. So that was this compound here. However, it's possible to do this, make the same compound using an ester. So in this example here, we have methyl benzoate. Notice that we are going to need, in order to get the 2 other rings, we're going to need 2 moles of phenylmagnesium bromide. And as before, the workup involves acid or water with a little acid. Okay. So the mechanism is again this nucleophile theme, because the Grignard reagent is a nucleophilic reagent. This carbon has a slight negative charge. This magnesium is a slight positive charge. So here's what the mechanism goes like for this. So we bring in phenylmagnesium bromide. Those electrons here are used to make the bond to the carbon. Electrons are bounced up onto the oxygen. So when that's done, we end up with O minus 1, 2, 3, 4, 5, 6, OCH3, and one of the phenols has now been bonded on here. What happens to the magnesium bromide? That now ends up as a counterion to the alkoxide. Now, since this is a derivative of a carboxylic acid, the typical pattern for this is that since this bond can be broken, we break, unlike aldehydes and ketones, this electron pair can come back and make a carbonyl group, but in the same process we knock out the methoxy group. So that then gives us, lo and behold, what we're left with is in fact benzophenone. And the other part is then the bromomagnesium methoxide is the byproduct. Well, notice now we have benzophenone again. which we had up here. So as we all know, that also reacts with phenylmagnesium bromide. And that will then bind on the third phenyl group. And then, of course, water and acid, H3O plus, will put the hydrogen on the oxygen and lead us to the final product. Questions about that? Yes. Yeah, sure. Maybe I can push it up. Oh, you're working on me. I'm trying to. Okay, I'm going to switch. This is sort of an old computer, and I had it rebuilt to the new operating system, so it's slow. Are there any questions? Okay, I want to review a couple things here first because it hopefully will bring things together. So, along with this theme of the nucleophile attacking the polarized carbon-oxygen double bond, here is the overall picture for all of the derivatives of the carboxylic acids, whether they're the acid chlorides, the anhydrides, the amides, or the esters. So in the case of the carboxylic acids, there's a carbon-oxygen double bond. There's a group W here, which will either have directly attached an oxygen or a nitrogen. This is unlike an aldehyde or a ketone where there's a carbon or a hydrogen here. So our nucleophile attacks the electropositive carbon, and we push a pair of electrons up onto the oxygen. Then, in the case of carboxylic acids, we go through this tetrahedral intermediate, but this CO or CN bond breaks. We have a leaving group, and that regenerates the carbon-oxygen double bond. And so we have swapped whatever Z nucleophile is for W. If we had an aldehyde or a ketone, then what happens is we get the same kind of reaction, but the CC bond or the CH bond is stronger and will not break. So this is the end point, except for the fact that it picks up a hydrogen ion and forms an alcohol. So there are two different outcomes depending upon whether you're a carbonyl group or a carboxyl group. This is the carboxyl group relating to the carboxylic acids. The carbonyl groups are the aldehyde and ketone stories. So that's the difference. And also the R prime group with a negative charge would not be a very good leaving group. Okay, so I'm going to... Can you see this? No, wait a minute, I think I can do something. Oh, wait, let me go back there. I've got to do something about this. Everything is so tiny on this one. When I put it on, maybe I'll just take this off. Yeah. Well, maybe we can just turn off the lights. Could somebody back there? I'm just going to go back because we don't have much time anyway. So. Could somebody, yeah, could you just switch off the lights here? Yeah, that might. Oh. That would help to plug this in when let's use this. There we go. A little better. Yeah. Okay, so here's our an acid chloride. We could react it with a water, an alcohol. If we react it with water, we'll go back, hydrolyze it to a carboxylic acid. If we react it with an alcohol or a phenol, we'll get an ester. If we react it with an amine or an amide, we'll get, an amine or an ammonia, we'll get an amide. So we've swapped those groups. Here's the same picture with starting with an anhydride. Always whenever you react with water, you'll get a carboxylic acid back. With alcohols or phenols, you'll get esters, and with amines or ammonia, you'll get amides. Here's our esters. The things that we talked about today, hydrolysis, making an alcohol and a carboxylic acid. We can swap out the alcohol group. That's called transesterification. The aminolysis reaction that we talked about earlier is this one. And we can also do that with other amines. Here's an amide now. Amides are actually the least reactive. Reaction with water gives us a carboxylic acid. This is a hydrolysis reaction. We react it with water, we break it up into the acid part and the ammonia part. We could react it with alcohols, not a particularly useful reaction, but we would get esters. Ammonia is going to simply change NH2 for NH2. That's not a useful reaction. We could react it with an amine. So those are some of the reactions with amides. And I think I will simply tell Dr. Olivanu that we went through sort of the beginning of that and then let him finish that for you. Are there any questions? I can send, would you like me to send you these PowerPoints?
Yes, please.
Okay.
Thank you.
Yeah. Hopefully they will be more